Hello, today we're going to give a peek behind the VMs you launch on Google Cloud into our storage infrastructure. My name is Dean Hildebrand, and I'm a technical director for storage in the Google Cloud Office of the CTO.
And I'm Denis Serenyi. I'm the tech lead for Google Cloud Storage.
All right, so in this session, we're going to answer a very simple question. How does Google Cloud scale your storage infrastructure? And it actually has a relatively simple answer. So, the first key point, and I really do think this is a very important point, is that there is a single infrastructure that underpins both Google services and Google Cloud. And so, Google Cloud customers and YouTube and Andrew Play Store services scale for the exact same reason, and that's because they're using the exact same underlying infrastructure. And next, we're going to dive into the details of Colossus, the file system that is at the core of this scalability, and talk about how Colossus abstracts out the complexities and messiness of the physical infrastructure to provide a highly performant, cost efficient storage infrastructure for Google Cloud's storage services. So let's take a step back. What are cloud regions? With 23 regions and 70 zones working together so seamlessly, it's sometimes easy to forget they're actually mapped down to a set of groups of physical data centers. And what's in these data centers? Pipes. Lots of pipes. But actually, okay, there's a little more as well. There's also lots of servers and storage because how else are you going to compute anything? So it's pretty straightforward, though, that when you launch a VM, let's say a 32 vCPU Skylake, it ends up running on one of our Skylake machines. And the operation of this is pretty fascinating. But one of the questions I get a lot from customers is how does our storage work? How does Google Cloud take our servers, disks, networks, and cobble them all together to provide such a wide range of storage services? And a typical follow up question is, does Google use the same infrastructure as Google Cloud? And of course, the answer is yes. But how does this work? So let's cover that as well. So, in this talk, we wanted to give a peek behind the VMs that you're launching to give some insight into how we build our storage systems here at Google. So you can have the confidence that your applications on Google Cloud can scale just like Google services. So, to begin, just like any well designed software system, all of Google is layered with a common set of scalable services. There are three core building blocks used by each of our storage services, and they are Colossus, Spanner, and Borg. And of course, there's many others, but in the interest of time, let's focus on these big three. So, first we have Borg, which launches everything from compute services to storage services and everything in between. And as you probably many of you already know, much of the learnings inside of Borg was all translated into Kubernetes when it launched. Second, we have Spanner, which is our globally consistent, scalable database that is used by Google services as well as our cloud customers as Cloud Spanner. And finally, we have Colossus, the beginnings of which started as the Google file system, which inspired many open source file systems such as HDFS. But since that time, Google has scaled a lot, and there's a lot more data to store. And so the need for this higher level of scalability really drove the creation of Colossus. And since this is a talk about storage, Denis is going to go deep into the details of Colossus in a few moments. And so to get back to this question of how does Google Cloud operate our storage, it uses these three core building blocks to provide the underpinnings for all of the storage services that you see, from Firestore to Cloud SQL to FileStore and Google Cloud Storage. Now, let's also get back to the question of whether Google uses the same school infrastructure and how does it use it? And the answer, of course, is that yes, it does, as I've stated already. And it does it in a pretty simple way, in the same way that the cloud does it. It takes each of the services that you see, from YouTube to photos, takes these same scalable building blocks and then layers on top of all of their needs to provide the level of availability, performance, durability that you're looking for in your storage systems. So this allows both Google services and Google Cloud customers to scale in the exact same way because they're using the exact same set of building blocks. And so, you can have confidence that if you go off and watch Cobra Kai, and there's also a million other people that want to watch Cobra Kai at the same time, then these three services are behind the scenes scaling to meet the needs. And traditionally, what's interesting is that much of the use cases into Borg, Spanner, and Colossus, and all of the innovation in them was driven by the Google services. But as our cloud customers have really scaled across the globe, they are now providing a lot of the innovation as well. So let's look at a typical flow. Let's say a user launches a GKE cluster onto a series of servers. So the VMs in that cluster get launched onto a series of the servers that they requested. And that's using Borg, by the way. And so then these VMs running on those services in the GKE cluster access their favorite storage services. Let's say they use persistent disk for their boot volume, and then they used file store and Google Cloud Storage for their unstructured data. Once they start accessing those services, the exact same big three building blocks, Colossus, Spanner, and Borg, are underneath the covers providing all of the services. So Borg is provisioning the resources for that storage system. Spanner is storing the metadata to say, for example, who can access the data and where is the data actually located. And then Colossus, of course, is providing all of the storage for the data. So now that we understand these three basic services, for the rest of this talk, let's deep dive into cloud storage and how it makes use of Colossus. So from the user point of view, Google has spent a lot of time and effort to try to make cloud storage as easy to use as possible. We want it to be as easy as filling up and emptying out an actual bucket. But behind the scenes, from Google's perspective, cloud storage is actually a massive distributed system that has the potential to take advantage of all of our regions, networks, points of presence, and all the servers and disks that I talked about earlier. And it has to make use of all those aspects to satisfy three primary use cases: content storage, compute analytics, and machine learning, as well as backup and archiving. And from the cloud perspective, we have lots of customers in each of these areas that are scaling using the services. So, for example, Box is delivering a lot of content to its users. The Broad Institute is constantly analyzing lots of different genomes every day. And the New York Times, you can find a really interesting article about how it's using Google Cloud Storage to archive its entire photo history. But Google Cloud Storage can scale to meet these needs because it's already been meeting the needs of our Google Cloud services, our services such as YouTube, Ads, and Photos, which archives a lot of photos. So in this talk, we learned about how Colossus is underpinning Google Cloud Storage, and it provides support for three very unique use cases. And now I'm going to turn it over to Denis so he can explain how does Colossus achieve all of this.
Thanks, Dean. So we talk a lot about GCS and how it can support a very wide range of use cases from archival storage to high throughput analytics, but we don't talk a lot about the system that lies under GCS, Colossus, which enables GCS's unique capabilities. So I'm going to dive into the details of how GCS uses Colossus and how Colossus works. We'll start from the top and work our way down. So I'm starting with the client library, which is how GCS interacts with Colossus. Actually, the client is probably the most complex part of the system. There's a lot of functionality that goes directly in there, for instance, software RAID, and applications can choose their own encodings based on application requirements. Applications built on top of Colossus, such as GCS, use a variety of encodings to fine-tune the performance cost trade-offs that they need to make for different workloads. The foundation of Colossus is its scalable metadata service called the Curator. It scales because clients talk to it only for control operations, for instance, creating a file, and because it can scale out horizontally. It can also scale massively because it's built on top of a NoSQL database called like Bigtable. In fact, the original motive Google had for building Colossus was that search was running into scaling limits, as Dean mentioned, of its predecessor, the Google file system. Putting file system metadata into Bigtable was the key trick that allowed Colossus to scale up by over 100x over the largest GFS clusters. Another way the system scales is that Colossus minimizes the number of hops for data on the network. Data flows directly between D servers, which is our really not very clever name for our simple network attached disks, and the Colossus client. Finally, Colossus includes background storage managers called custodians, which handle things like disk space balancing and RAID reconstruction. They play a key role in maintaining the durability and availability of data, as well as ensuring the storage system is working efficiently. So that's Colossus in a nutshell. Here's a picture of what a typical Google cluster looks like. The key ingredient is having this shared storage pool managed by the Colossus control plane. This large disaggregated storage layer is able to support a wide variety of applications on the same underlying physical resources. And each application has the rough illusion of having an isolated file system. In aggregate, we're talking about really big scale here. A single cluster is scalable to the exabytes of storage with tens of thousands of machines. And what I've drawn here represents a typical mix of internal Google services. You've got some YouTube serving and maybe some ads map reduces, together with GCP VM instances using GCS, all together sharing the same underlying Colossus file system. So it's really the case that the same storage system that's driving these global scale Google applications is also driving our customers' cloud workloads. The scale, disaggregation of resources, and variety of workloads is the key to driving efficiency and lowering costs. For instance, we can provision to the peak demand of low latency workloads, like maybe this YouTube serving workload here, and then run batch workloads like MapReduces and other analytics more cheaply by having them fill in the gaps of otherwise idle time. Another great thing about Colossus is it abstracts away a ton of complexity that storage-intensive applications would otherwise have to deal with. For one thing, frankly, our data centers have a tremendous variety of underlying storage hardware. When we're adding capacity to the system, we're always buying the disk of the day, which is whatever disk currently has the lowest total cost of ownership. And same goes for flash. And these devices last a long time, which means that each cluster will have many disk sizes and types. Add to that the fact that applications have different requirements around durability, availability, and latency. Colossus addresses that by providing service tiers and allowing applications to specify erasure codes tuned to their needs. And add to that, at Google scale, some hardware is failing virtually all the time. That's just a testament to the scale that we're operating at. It's not like the hardware is unreliable. It's just that there's a lot of it. So dealing with some failures is the common case. Colossus steers I/O around these failures and does fast background recovery to provide highly durable storage within the cluster despite all of this chaos. The end result is that for GCS as well as Google's own services, these hardware resources and their associated complexity are totally abstracted away. Systems provision bytes and I/O as abstract, undifferentiated units. That makes using storage very simple for all the applications we're running. So now let's deep dive into how Colossus helps ensure the storage pool is being managed efficiently. I mentioned that applications built on top of Colossus can provision bytes and I/O as abstract resources. But as you might imagine, it involves a lot of magic to ensure that all the I/O and all the bytes are available when applications need them, but also not over provision either of these things, because that would mean a lot of waste. Under the hood, we take advantage of the fact that data has a wide variety of temperatures, as we're trying to illustrate here. We mix in flash, not always to lower latency, but simply because flash is the most efficient way to serve really hot data. If we do our job right, we buy just enough flash to push the I/O density per gigabyte for the remaining data into the range that can be served by disks. And then we buy just enough disks so that we can fill them all up. If we do this well and have the right mix, we end up with really efficient storage. Now let's talk about how Colossus maximizes storage efficiency for disk-based storage. Within our population of disks, as I mentioned earlier, we're going to have a wide variety of disk sizes. To maximize efficiency, we'll want to do two things. We'll want to keep the disks full, because empty bytes are just excess inventory. And we want to keep the disks busy, so we're not wasting that disk spindle. Because each cluster has this roughly the same I/O bandwidth, what this means is that because each disk has roughly the same I/O bandwidth, what this means is that we'll have to keep hotter data evenly spread across all the drives in the cluster, and then we just fill up all the remaining space on each drive with cold bytes. To make this work, the key problem that Colossus has solved is placing data intelligently. Turns out, newly written data is typically hotter, so Colossus spreads new writes evenly across all the disks, leading to a pretty even balance of hot data. And then Colossus's background rebalancer moves older cold data to bigger drives. This works great for analytics workloads because analytics data typically cools off as it ages. Now, a lot of this stuff was developed and refined over the years so that Google can run its own services, search, ads, YouTube, etc., all those services that Dean was talking about, at massive scale as simply and efficiently as possible. But for cloud, this means that cloud users can also leverage this functionality, and you end up with simple and inexpensive storage. Okay, so this is a picture of one of our internal dashboards used to monitor and debug storage performance in a cluster. There's a lot of boxes in this visualization. Each of those small boxes is a D server, and they're sized by disk capacity and colored by spindle utilization. When it looks like this, we're really happy. Basically, the whole cluster is really busy. That's why it's looking all red like that. So we're getting all the value out of our disk spindles. Sure, there's some darker colors sprinkled in there, but it turns out those are D servers that are down for maintenance or being decommissioned. So that's Colossus in a nutshell. Now let's pop the stack and talk about GCS itself, which is really just a layer on top. It turns out GCS is employing a lot of the same tricks that Colossus uses, just at the region and multi-region level. To illustrate how they're similar, here's a simple representation of a GCS deployment in one of our GCP regions. In this example, we've got 3 clusters, each with a GCS instance on top of Colossus storage. First off, GCS employs some of the same hot data placement techniques used by Colossus, placing data close to where it's likely to be read, and also caching data to minimize network distance and lower latency. And just like Colossus is rebalancing colder data within the cluster, GCS rebalances colder data between clusters in the region to make sure we're able to fully utilize all available space, as well as ensuring that data is always durable and available in the face of disruptions or failures in the underlying infrastructure. GCS kind of thinks of each cluster in Google's fleet as an abstract disk. And by managing these clusters intelligently, it's able to handle all the diverse workloads that users bring to GCS, like content serving and archival and analytics, and do it efficiently. The way we think of GCS is that it's Colossus in the cloud. So to wrap up, we know about GCP's scalability. What we uncovered today is that GCP can scale because it's built on top of these core Google services that are battle tested and have demonstrated the ability to scale to pretty massive levels. In fact, GCS is just a layer on top of Colossus, which is the cluster level file system that doesn't just handle the storage needs of GCE VMs, GCS content serving, etc., but also handles all of Google's internal storage needs from search to maps, YouTube, photos, etc. And lastly, we learned that there's a ton of complexity under the covers of GCP, but systems like Colossus have abstracted all of that away, allowing GCP customers to just focus on their business. So to wrap up, I want to give a big thanks to Dean for being my partner in crime for this deep dive into what lies under the hood of storage at GCP.
Hey, Dennis, glad to be that partner. And thanks a ton for sharing your extremely deep knowledge in Colossus and Google Cloud Storage. And I really hope this gives our customers confidence that by using this underlying scalable infrastructure, that they can scale their applications as big as they're looking for.
Thanks a lot. I hope you found this as interesting as we do and that you learned a lot. Have a great day.